Hi everyone. Thanks for watching this video. I'm sorry I had to cancel the class, but I don't think it will be a regular thing. Before we start, I just wanted to remind you of a couple things. We had assignment 1 due on Wednesday, October 4th. Obviously, I've canceled that class, and so the new due date is Thursday, October 5th. And I'd like you to just please bring your assignment and hand it in at the start of your lab section on Thursday. Also, assignment number 2 will be posted on the course website sometime this week. So, what we've been working on the past couple of weeks is solving for the transient response of a current in a circuit. And we specifically looked at the RC circuit and the LRC circuit. For the case of the RC circuit, we analyzed that problem in full detail and we actually solved the differential equation. For the LRC circuit, the differential equation was more complicated. It was a second order differential equation. And so what we did instead is try to use some insights that we had from a mechanical analogy to the LRC circuit to kind of deduce some of the characteristics of the solution. What we're going to do today, actually before I get to that, when you do assignment 2, what you're going to do is you're going to analyze the transient response of an LR circuit. And so what I encourage you to do when you encounter that problem is to look at your notes and then kind of follow the strategies that we used for solving the RC circuit. Just apply those strategies to the LRC circuit. Okay, what we're going to do today is we're going to shift gears a little bit and we're going to ask the question, if we have a circuit that's been driven by a sinusoidal signal, so for example, we use a function generator in the lab to provide an oscillating signal, how does the current in the circuit vary as we change the frequency? So our function generators have a frequency knob, and so how does the current change as we tune that frequency? Okay, so what I want to do is talk about the RC circuit frequency response. Okay, and so the circuit that we're going to look at has just two components. It has a capacitor and a resistor, but this time, instead of being driven by a battery with a switch, what we're going to do is we're going to drive our circuit with the output of a function generator. And so the output of the function generator will be the input to our circuit. And so I'm going to call that V in. It's going to have some amplitude V naught, and it's going to have sinusoidal oscillations, and those oscillations are going to occur at an angular frequency of omega. And when we do that, we'll establish some kind of current in our circuit, and we want to solve for that current. And then maybe what we'll do is maybe we'll look at the voltage across the resistor with something like an oscilloscope. And so if we know how the current is varying in a circuit, then we could calculate the voltage of the resistor just from I times R, the voltage across the resistor. Okay, before we do the analysis, I just want to remind ourselves about the meaning of the amplitude and frequency or angular frequency of our sinusoidal signals. And so I want to make a plot here, and the plot is going to be time on the horizontal axis and then V in, which is V naught sine omega t, on the vertical axis. So if we were to plot a sine wave, it starts at 0 at t equals 0, and then there is an oscillation that looks something like this. Okay, and so I want to label some of these things. We would say that our sine wave has an amplitude of V naught. That means it oscillates between plus V naught and minus V naught. Sometimes people talk about the peak-to-peak voltage. And so the peak-to-peak voltage, sometimes denoted P2P, is just twice the amplitude, so twice of V naught. Okay, and so that's what the coefficient V naught indicates, is the size of the signal. And then we could also talk about the time that it takes the signal to complete one full cycle before it repeats that pattern. And so that time is called the period T. Okay, and so here what I'm looking at is the time between crossings of the horizontal axis with a positive slope. Okay, and so that's one full cycle. Okay, so then we can say that the V0 is the amplitude and T is the period, which is the time to complete one full cycle. Okay, this period can be related to the frequency. So the frequency F is, well, let's write F equals 1 over T is the frequency. The period has units of seconds or time because we're measuring the length of time that it takes a signal to complete a full cycle. And so that means frequency has units of 1 over time or 1 over seconds. And so that's often denoted as hertz. So frequency is measured in hertz. The angular frequency is 2 pi times f, which is equivalently 2 pi divided by the period. And so this is the angular frequency. And so when I write down omega in sine omega t, omega is really 2 pi divided by the period, isn't another way to think of it. So the units of angular frequency is 1 over seconds from the inverse of the period or from the factor of f, and then 2 pi is measured in radians, and so this is measured in radians per second. Okay, so I want to make a couple of observations from some of the things that you looked at in lab number 2. So if you remember back to the final part of lab number 2, you actually built this exact circuit. You had a function generator in series with a capacitor and resistor. If I remember correctly, the resistor was something like 10 kilo ohms. The capacitor, I think, was a nanofarad. And the frequency was 16 kilohertz. And some observations that we might have made, observations from part 4 of lab 2. So one is that the current, or equivalently the voltage across the resistor, which is just I times R, so it's the current times a constant, also oscillated sinusoidally. The current also oscillates sinusoidally. And in addition to that, it had the exact same frequency as the voltage oscillations. So the current also oscillates sinusoidally and has the same frequency as Vn. So whatever frequency you set on the function generator, your current will oscillate at that same frequency. Okay, the other thing you would have observed is that when you plotted the voltage across a resistor, which is proportional to the current, it was shifted in phase with respect to both the output of the function generator and the voltage across the capacitor. So that means the current is out of phase with Vn. So there's a phase shift between the current and the output of the function generator. One thing that maybe we didn't observe, but I'll point out now, is that you were told to do your circuit, do your measurements at 16 kilohertz. If you would have changed the frequency, you would have found that the phase of that current would shift with frequency. So the observed phase depends either frequency or angular frequency. Okay, and another thing that you may or may not have observed is if you change the frequency, you would have found that the amplitude of the voltage across the resistor, or equivalently the amplitude of the current, would also depend on frequency. So the amplitude of the current depends on omega. Okay, so based on these observations, what we're going to do is we're going to assume that the current in the RC circuit is of the form. Okay, so what are we going to have? The current is going to have an amplitude, and I'll call the amplitude I naught. And we said that that amplitude is going to change with frequency. So I'll put that in explicitly. So I'll put in the frequency dependence. And so this is our frequency dependent amplitude. Okay, we said our current would oscillate sinusoidally, so there'd be some sine function in there. It has the same frequency, so I'll put in the omega t, and so this is the same frequency as Vn. But we said that there would be a phase shift, and so the way we can incorporate the phase shift is to add a plus phi. I'll use phi for our phase, and we said that that was also going to depend on frequency. And so this was a frequency dependent phase. Okay, so that's what we think our current is going to look like, and our task is to find how I naught and phi vary with frequency. So our goal is to determine how I naught of omega and phi of omega depend on frequency and the circuit components. So by circuit components, I mean like the value of the resistor and the capacitor that we use. Okay, so all we're going to do is we're going to start in the same way that we always do when analyzing circuits. We're just going to do a Kirchhoff voltage loop rule. And so if I do a loop rule, maybe I start in one corner and I navigate clockwise around the circuit. So if I start in the bottom left corner, the first thing we do is gain the voltage of the function generator Vin, and then we drop a voltage across the capacitor and drop a voltage across the resistor, and when we add all those things up, they have to sum to 0. So the Kirchhoff voltage loop rule requires that Vn supplied by the generator minus the voltage lost across the capacitor minus the voltage lost across the resistor have to total 0. But we know that the voltage across the capacitor is equal to charge divided by C, and we know that the voltage across the resistor is I times R. And so those have to be 0. So what we're going to do is we're going to actually take a time derivative of this expression. What that's going to do for us is it's going to convert this charge into a current, and then the current into a di dt, and then we'll have a differential equation in terms of the current. Okay, so we would have something like dvn dt. At the same time as taking this derivative, I'll take the two other terms on the other side, on the right-hand side, to get rid of the minus sign. So we'll have a 1 over c dq dt, but I'll write dq dt as I. And then we have a plus r di dt, like so. I'm going to call this equation number sign because we'll come back to it. And so now we're again in the situation where we have a differential equation. This time, instead of in terms of the charge Q, it's in terms of the current I. Okay, so how are we going to make some progress? Well, what we're going to do is we're going to take advantage of some of the things that we already know. We know that Vn is equal to V naught sine omega t. And so that means we can just evaluate the dVn dt derivative directly. dVn dt. So we're just taking a derivative of sine, so a factor of omega will come out. We'll get V naught, and sine becomes a cos, and then we have omega t. So that's it. The other thing we know is that, or let's say the other thing we've assumed is that the current is of the form an amplitude times sine omega t, the same frequency, but plus a phase factor. We have a di dt, and so if we're assuming a certain form for the current, then we could take its derivative. Again, a factor of omega comes out, the sine becomes a cos, and that's it. So we're going to take these results and we're going to sub into the differential equation above. And that will just get rid of all the derivatives, and we'll just be left with an algebraic equation that we could try to manipulate. Okay, so let's do that. Maybe I'll make this a bit smaller so we can see equation number sign, and we'll make our substitutions. So first thing, we have the derivative of Vn, so we'll have omega V naught cos omega t is equal to, let's see, 1 over c times I. So we'll have an I naught over c, then we'll have sine omega t plus phi. And then we have plus r times di dt. So we'll have omega I naught, we'll pick up a factor of r, and then we'll have cos omega t plus phi, like so. Okay, the next step is to, we can't really do much with this expression because we have, trig functions that don't have necessarily the same arguments. So we have sine omega t plus phi, we have cos omega t, we have cos omega t plus phi. It's really difficult to do anything with this until we make use of some trig identities. So we're going to use the following trig identities. So one of them is that sine omega t plus phi is equivalent to sine omega t cos phi plus cos omega t sine phi. And we're going to use one other one. We're going to use the identity for cos omega t plus phi. And that is cos omega t cos phi minus sine omega t sine of phi. Okay, and so, I think you can see what we're going to do here. We're going to use this identity for the cos omega t plus phi factor, and we'll use the first identity for the sine omega t plus phi factor. Okay, so let's see what happens when we do that. Nothing happens on the left side, so we still end up with omega v naught cos omega t is equal to. Okay, so now we're going to have I naught over c, and then I'm just going to write that identity out. I'm not going to make any other changes. So we'll have sine omega t cos phi plus cos omega t sine phi. And then we have plus omega I naught r, and then we'll just write out the other identity. Cos omega t cos phi minus sine omega t sine phi. All right, And so it's not clear yet why this is a useful thing to do, but if we look at this a little bit carefully, what we can find is that now what we have are some common factors. We have a cos omega t factor on the left, and we have a cos omega t on the right, and then we have another one on the right. So we can collect like terms. We could also do that for the sine omega t's. We have two sine omega t terms. They're both on the right-hand side. Previously, we wouldn't be able to do any of this because we had like cos omega t plus PHYS and sine omega t plus PHYS. It wasn't possible to combine any terms. Okay, so we could re-express this. Let's start with the sine omega t part. So what multiplies the sine omega t? So we have a sine omega t, and then we're going to have an I naught over c cos phi. That's the first term on the right-hand side. And then what multiplies sine omega t in the second term is a minus omega I naught r sine phi. Okay. And then what about the coefficients of the cosine omega t? Well, what I'll do is I'll start on the right-hand side, and what multiplies the cos omega t is an I naught over c sine phi. And the second term is plus omega I naught r cos phi. And now we have to be careful because we also have a cosine omega t term on the left. I'm going to move it over to the right, so we'll pick up a minus sign, and then what multiplies that cos omega t is minus omega v naught. Okay, good. And so all of that will have to be equal to 0 because we took the term that was on the left-hand side and moved it over to the right. So there's just a 0 left over. Okay, now here's where we'll make use of some insight here. The first insight is that this expression that we've just written above must be valid at all times. Okay, but there is a particular time where the sine omega t term is going to be 0 and the cos omega t term is not 0. For example, t equals 0 is going to be, sine is going to be 0 and the cosine will be 1. So at some particular times, we will have let's see, sine omega t is equal to 0 and cos omega t is not equal to 0. Now, this expression is still valid in that case, but the whole first term will vanish because it multiplies sine omega t, which at some times is going to be 0. And so the only possibility is that everything that multiplies the cos omega t, which is non-zero, so everything in these blue brackets here has to be 0 in order to satisfy this equation. Okay, so at these times, we require, well, it would be I naught over c sine phi plus omega I naught r cos phi minus omega v naught equals 0. Okay, so I'll label this as equation 1. And in fact, equation 1 has to always be true because there's nothing in here that is, you know, if it's true at some time, it has to be true at all times, okay? So what we can do is we can continue with this kind of logic, and we could say, well, at another time, well, let's say at other, because it's not just one time, but there are other times, what we're going to have is the opposite case. We'll have cos omega t is equal to 0, and sine omega t is not equal to 0. And if we go back to this big equation, what we would say then is that, well, the cos term is going to vanish because we're going to assume there are some times where cos omega t is 0, and sine omega t is not 0. So now, in order for this equation to be satisfied at these particular times, everything in the green brackets has to be 0. Okay, so therefore, it must also be true that, so what was in the green brackets? I naught over c cos phi, I naught over c cos phi, and then it would be minus omega I naught r sine phi. Okay, so minus omega I naught r sine of phi. And so that has to be 0 as well. And so we'll put this one in a different color box, put that in a blue box, and we'll say this is equation 2. In fact, equation 2 only has 2 terms. The I naught is a common factor, and so we can divide by I naught and replace it with a 1 in those 2 terms. And so we have 1 over c cos phi minus omega r sine phi is equal to 0. Okay, so now we try to solve equations 1 and 2 for phi of omega and I naught of omega. Notice that what we have here, we've managed to create a system of 2 equations and 2 unknowns. The 2 unknowns are the phase and current amplitude, and so we should be able to solve for these 2 unknowns. In fact, we're going to start with equation 2 because it's the easier one. So let's start with equation 2. We've already canceled the I naught, and so what we can say is 1 over c cos phi must be equal to omega r sine of phi, and that implies if we divide by cos phi and divide, let's do this. Let's divide both sides by, I'm going to say omega r cos phi. So on the left-hand side, the cosines will cancel, and we'll get 1 over omega rc is equal to, and on the right-hand side, the omega r factors will cancel, and we'll have sine over cos, but that's just tan of phi. And so therefore, we've already got 1. We can say the phase is equal to the inverse tangent of 1 over omega rc. And so this tells us how the phase of the current varies with frequency in our RC circuit. So this is the frequency dependence of the phase of the current. Okay, if we look at equation 1, that is a little more difficult to work with because there's no obvious cancellations. We can't cancel the I naught factor because we don't have the I naught in the third term minus omega v naught. We can't cancel any phase factors because we have a sine phi and a cos phi and so on. So we have to be a little bit clever here. And let's go back to return to tan phi, which we know is equal to sine of phi over cos phi. We also know that if we had a right angle triangle, that tangent is the opposite over the adjacent, right? It's toa in Sakatoa. And then we also know that for our RC circuit, tan phi we worked out had to be equal to 1 over omega RC. So our strategy is to make or construct, let's construct a right angle triangle with the opposite side equal to 1 and the adjacent side equal to omega RC. Then if we calculate tan as opposite over adjacent, we get the correct 1 over omega RC that we require. Okay, so what would that look like? Maybe we have something like this. This is our right angle triangle. This would be phi, and then on the opposite side, we'll say that that's equal to a length of 1, and on the adjacent side, we'll say that that has a length equal to omega RC. Okay, well, what does that mean then? Well, that allows us to then calculate the hypotenuse, which from Pythagoras' theorem is opposite squared plus adjacent squared all square root. And so that would be the square root of 1 squared, which is just 1, plus omega RC squared. Okay, so that's just a requirement of a right angle triangle, but the nice thing about this is now we can say, well, sine of phi is, soc. Its sine is opposite over the hypotenuse. The opposite side is 1, and the hypotenuse is the square root of 1 plus omega RC squared. Likewise, we can say cos phi, ka is adjacent over hypotenuse. The adjacent side is omega RC, and the hypotenuse is 1 plus omega RC squared again. What we can do is, let's call this A and B, and we can go back, and we go back to equation 1, and for sine of phi, we're going to sub in A. And for cos of phi, we'll sub in B. And then that's going to leave us with an equation where the only thing that we don't know is the current amplitude. And so we can solve for it. So what our plan is to sub A and B into equation, I think it was equation 1. Okay, so let's give that a shot. Equation 1, let me just rewrite equation 1 just so I don't have to scroll up and down all the time. So equation 1 rewritten was I naught over C sine phi plus omega I naught R cos phi minus omega V naught is equal to 0. Okay, and so let's just make those substitutions. So I naught over C, and instead of sine phi, we're going to write 1 over the square root of 1 plus omega RC squared. And then we have plus omega I naught R, and instead of cos phi, we're going to have omega RC over the square root of 1 plus omega RC squared. And then we still have the minus omega V naught, and all of that has to be equal to 0. Okay, so all that's left to do is to solve for I naught of omega. And I'll leave that as an exercise for you to do. It's just some algebra, but what we can do is we can say that this will be an exercise, for the student to show that I naught is going to be equal to omega v naught over c divided by the square root of 1 plus omega rc squared. And that's it. I know this equation above here looks complicated, but what ends up happening is we get a fair bit of cancellation, and things boil down and reduce to this expression in the box, which is how the current amplitude I naught varies with frequency, say omega. Okay, good. Just looking ahead a little bit, part of the point of this exercise was to show that analyzing a relatively simple circuit is just an RC circuit after all. Where did we draw it? We drew it right here. It's just a circuit, series combination of an R and a C. And it took us like, I don't know, 1, 2, 3, 4, 5, at least 5 to 6 pages of analysis to solve for the amplitude and phase of the current. And so it was quite a bit of work. The steps weren't that hard, but we had to be a bit clever, like in constructing right angle triangles and so on. We still ended up having to solve essentially a differential equation. We had to guess the form of the solution for the current. So what we're going to do going forward is we're going to try to develop some techniques that will make solving these problems much more efficient. And that's going to require some preliminary work. We're going to have to introduce complex numbers, and we'll have to look at Taylor series expansions and so on. And so that's just looking ahead a little bit. So I've got about, 14 or 13 minutes left here. And what I want to do with that time is just do a bit of a preview of lab number 3, I guess. So lab number 3 preview. So for lab number 3, what we're going to do is we're going to study some of the transient analysis that we have looked at before. So if you recall, the problem we solved was charging a capacitor through a resistor. Okay, and what the circuit looked like was we had a battery instead of a function generator, and then we had our switch here. Here, let's get it like here. Here's our switch, and then we had our resistor and our capacitor, like so. And so suppose this is battery has voltage V naught. Here's our switch S. Here's our resistor R. Here's our capacitor C. And then maybe what we do is we look at the voltage across the capacitor, maybe with an oscilloscope or something like that. And what we found was that VC of t, was equal to this thing. It was V naught, and then it was 1 minus e to the minus t over tau, where tau was an RC time constant. Okay, and if you plot that, what we'll see is, as a function of time, the voltage across the capacitor, for the case of a charging capacitor, looks something like this, where it asymptotically approached its new equilibrium at a voltage V naught. Okay, we didn't do it, but if we were to solve a discharging capacitor, so if we were to discharge a capacitor through resistor, that circuit might look like the following. So maybe we have our resistor and our capacitor, and this time we get rid of the battery and we just have this, something like this, R and C. What we have to do now is we have to assume that initially the capacitor had some non-zero charge, right? If it was initially uncharged and then we close the switch, nothing would happen. There's no charge to remove from the capacitor. So we assume that initially the capacitor is charged to some voltage, and then we measure the voltage across the capacitor after we close the switch. So we say the capacitor is initially charged to, say, some voltage V0, and then what we're going to do is we're going to close the switch at time t equals 0. If we did that, the solution for the discharging capacitor, which, you know, many of you have probably seen before, I think we did it in 121 last year if you took 121 with me. The solution is the following. It's just an exponential decay where tau is the same RC time constant. If we were to plot that, what it would look like is the following. So Vc of t, let me redraw that. So this is Vc of t is equal to V0 e to the minus t over tau. And it starts at t equals 0 at a voltage of V0, and then it decays exponentially. It looks something like that. Okay, so one thing you're going to do in the lab is you're going to build a circuit that, instead of using a switch, so in the lab, you will construct the following circuit. Okay, so we'll have our R and our C like so, and then we'll look across the capacitor with the oscilloscope. And so R and C. And then what we'll do is, instead of using a switch, we're going to use the function generator, but it's going to be in square wave mode. So the function generator is set to a low frequency square wave. So the square wave is half the time low and half the time at some high voltage. When it's low, it's like discharging the capacitor, like there's no battery there, the voltage is just at 0. And when it's in its high state, it's like you put a battery of V0 in there and then the capacitor charges. So by having a low frequency square wave, and by low frequency I mean enough time for the capacitor to fully charge when the square wave is at some positive voltage, and then enough time to fully discharge when the square wave is at a low voltage. So what we expect to see then is, if we were to plot as a function of time our square wave, maybe it starts positive and then goes down to 0 and then jumps back up to positive. So this would be our function generator. And then what's our capacitor going to do? Well, it's going to charge up. Let me see if I'm going to get it to charge a bit quicker than that. So it charges up and reaches some saturation, and then it discharges and goes to 0, and then charges up and reaches its saturation up here somewhere. And so this is the voltage across the capacitor. And so this is what you're going to see in the lab when you set up your circuit. And the goal is to make a quick estimate of the time constant. Goal is to make a quick estimate of the time constant tau is equal to r times c. So of course you're going to know the values of r and c that you're using, so you could just calculate the expected value. R is going to have 5% uncertainty, and c will probably assume a 10% uncertainty. And so you want to see if your experimentally measured value is in agreement with what you expect. So to estimate tau, we're going to find the value of the voltage across the capacitor when t is equal to tau. Okay, so what's that going to do for us? We know that Vc is equal to V naught e to the minus t over tau for the discharging case, and that's the case I think we'll focus on. So therefore, when t is equal to tau, we have Vc t is equal to tau is equal to V naught e to the minus, and for the time we just have to put in tau, and then we have to divide by tau, and so we end up with V naught times e to the minus 1, which is V naught over e, and 1 over e is 0.368 times V naught. So what you're going to do in the lab is you're going to set up the circuit that we drew, so this thing with the square waves. You're going to adjust your oscilloscope display so that you focus in on one of the discharges. And when you do that, what you're going to see is, for the capacitor voltage, Vc of t for the discharging case is going to start at some maximum and it's going to decay down, like so. So what I want you to do is to find the peak voltage, which maybe we'll call V naught, and then find where on that curve does, like where do you encounter V naught over E, which is 36.8% of V naught. And once you find that vertical position, then you just go down and you'll say that occurs at the time t equals tau. So once you find that time, you just know that that is equal to the time constant, and I want you to compare the measured value to r times c. So you should have an experimentally measured tau plus or minus delta tau and a calculated value of Rc equals tau plus or minus that calculated value of tau, and see if those two overlap within uncertainty. That's all part one of the lab. In part two, you're going to build a similar circuit, but you're going to use the one of the multimeters that can be programmed to log data for you. And so the lab manual will take you through a process to program this multimeter so that when you initiate a capacitor discharge, it'll log the data for you every 0.2 seconds. It'll measure the capacitor voltage, and then you'll end up doing some analysis of that data to find a second, more careful measurement of the time constant. Okay, thanks very much. That's where I'm going to stop. And I will see you next week. Again, Monday there's no class because it's Thanksgiving, but I will see you on Wednesday. All right. Thank you very much.